ask Cyril now to open our class with a word of prayer.
Let us pray. Almighty and living God, we are humbly asking for your blessings for our class today. May you guide and supervise us from above, and may you protect us from our unseen enemies. Help us win our battles in life, and may you honor us with the presence of your divine spirit. We bring back all the glory and honor to you, Lord. Amen.
Amen. Thank you so much, Cyril, no, for leading us in prayer today. I am offering, no, we are always offering, no, our safety, no, and it seems that not only we are facing the physical battle there, no, in Europe, but even spiritually, probably, no, I don't know if you believe on spiritual battle, no? But that's what we are experiencing, no? Some Christians believe in spiritual battles, no, and however, no, may God, no, always protect us in this area. Now, I've checked some of your names already, no, so for your attendance, I think I will add the name of Mr. Famadico, no, Ryan Aguilar and Ayan Tihada, no, are not still here, no. So for now, amo lang ang aton attendance. And we will be moving on to our lecture. No? And what is our chapter 4 again? No? Who was raising the hand a while ago?
Ako, sir.
Yes, you can go ahead. No?
Chapter
Yes.
4, sir. Current, resistivity, and resistance.
Okay. So current, resistivity, resistance, and from this lesson, no, what have you got? No? Ano yung mo nakuha? No? I think some of these things, no, we've discussed it last week. No? Ira, can you tell us a little of what you understand of chapter 4?
About the electric current, sir.
Okay, so what is with electric current again, no, that you got, no?
It is the continuous flow of electric charges in a conducting path, sir.
Okay, it's a continuous flow of charges, no? So maybe, one thing in our mind that there are electrons that are moving there, no? So thank you, no? Thank you, Ira, no, for that answer, no? So it's a continuous flow. So it means that since there's a continuous flow, there must be a source for it, no? So if there's a continuous flow, now who can tell me the source? Now, where does the charges come from? No, in order for you to have a continuous flow of charge, no, in a wire, so where does it come from? Anybody would like to try? No? Where is our source? No? Anybody? Yes, Jessary?
From the battery, sir.
Okay, so again, no, who discovered the battery, Jessary? So we know that it was discovered by whom? The battery. Anybody? So his name was, no? His name was?
Alessandro Volta, sir.
So we have Alessandro Volta, no? So you must have a source, no, in order for you to have a steady and continuous supply of these charges. Otherwise, no, the charges, no, will not actually move in the wire, no, unless something pushes it. So here is a picture of a battery, no, and partly, no, or at some point we already discussed that, no. Now we will also understand, no, that our battery, no, that we know today are rechargeable, no. So perhaps in this day and age, during that electrolyte, no, what you have there is a solution, and that solution eventually, no, will accumulate charges, and these charges, no, will start to produce the current already, no. But what we know also today is that once this battery is depleted of charges, we have it's a common knowledge already that we can recharge it. No? There are batteries that are rechargeable. No? So maybe as we discuss along, we will see the dynamics also, or how is it possible to charge a battery, or what should be the condition when the battery is rechargeable, that what are you going to do to be able to charge such a battery, rechargeable. So we understand that there are batteries today that we can use again and again, maybe after a certain lifespan, and when it is exhausted, that's the time you will replace it. But it's not used only one time, and then you throw it away. So rechargeable kinds of battery, and this is a very handy thing. It allows us to use the battery for a long period of time. And our current, by the way, is a rate of flow. So we measure it in terms of Q all over T. So charges over time. So our unit of current, which is ampere, can also be written as 1 coulomb per second. Now, from this equation last time, we were able to calculate Q, and we know Q to be I times T. So what we did was we multiply the denominator. So we can actually multiply these two and get the product I times T to give us also the variable Q or the charge. So that's another way of looking at our expression. Now, if you also remember, so we also equated some kind of an equation called work. And we equate it as BQ last time. So I do hope that you can still remember that. And we also give it a name, since work and energy are synonymous, that electrical energy can also be written as VQ. And we can eventually maximize this energy if the charges bring them, that we can transfer this energy to some remote locations or some far distances because of the charges that are bringing this energy. Now again, we can attach over this one the value of Q to be the product of I times T. So eventually, if we will symbolize energy as E, simply E, then if Q is I times T, then we can substitute Q to be IT, and then therefore now we can have again energy to be a value that is VIT. So we will just have this for the time being, and we will reflect on it later on. We've derived this already some time ago, and we will just make use of that as we move along. So have that in mind. And we also learned last time that our wire, there's always this opposition in the flow of the charge in the wire. So we call that resistance as we call that opposition as resistance in ohms. So our value of resistance, which we give a unit of ohms, is affected also by a number of factors. So here is the term we call resistance. Now we are going to relate that resistance, since we already have the variables V, and usually V can be related to the voltage. And we have also I, which we relate as current, electric current. And then we also have this variable R, which we call as resistance. So V, I, and R are the three other variables that we could relate with each other. Now, resistance again is a property, probably. It's a kind of a property. It is present in a given metal or conductor. no matter what kind of conductor you have, no? There's always it's a degree of resistance. Maybe, it varies from one metal to the other, no? There are metals that have less resistance, no? Uh, as as uh, as uh, as that kind of material is better conductor than other materials, that its resistance may be lower or greater, no? But generally, all metals, no, do have, no, resistance. Now, we call the resistance there as the opposition. No? It's the property of a material to oppose the flow of electrical charges, no, or a metal, no, its natural tendency to oppose the flow of charges. So similar probably to the idea of friction, we have this thing called resistance. So notice, no, when something is sliding over a surface, we notice that it will come to a stop eventually, because there's always this friction, no, frictional force that exists between two surfaces that come in contact. Now, similarly, charges, when it passes through a wire, it encounters this opposition. So if the opposition is so great, most likely the charges will move, very, very slowly. Now, these values V, I, and R, these variables V, I, and R can be written in an expression, and the expression, we can come to know of this expression already as Ohm's law later, but R, is a certain constant that you get, whenever you divide the voltage in a wire, by the current that passes in the wire. So there's always this constant ratio whenever you divide V by I. And that ratio, according to this one, will be called as resistance. Now, our units, that is denoting, each of this. So for voltage, we will have the unit volts, and it is symbolized by letter V. Our next unit is the unit in ampere, and it is denoted by capital letter A. And finally, your last unit here, resistance, which is in ohm. And again, the symbol for ohm is the omega symbol. So we have here an omega notation, which is probably looking like that. And again, maybe we will see the symbol there. So again, we have the three factors here, or the three variables that relates with each other to get a certain unit. Now, more familiarly, Ohm's law is written in terms of the product of I and R as a value. So this thing called resistance, ladies and gentlemen, was given a name by a physicist. Again, his name was Georg Simon Ohm. So Georg, or George Simon Ohm, is, I believe, a German, if not an Austrian guy, and that's why that's how they pronounce his name. But I'm trying to delete this. Now, ang unit of current was named after Andre Marie Ampere. So another physicist as well. I think he's a French physicist, and that's the unit of current attributed to him. Now for this variable called resistance, so if we will consider the wire, guys, three factors actually affect the unit resistance, and here are these three factors. So first, they say that there's resistivity that is present actually in the material or in the metal. So every metal has different resistivities. So that's one factor that affects the resistance of the wire. Another is length. if the wire is longer, no? So if we have here, no, on this side a wire, the longer is the wire, no, they found that it is directly proportional to resistance. However, its area, no, is inversely proportional, meaning the wider is the area or the cross section of the wire, no, then they notice that the resistance gets lower. So resistance and area are inversely proportional. But these are the three factors, no, that eventually affect the resistance of the wire, no, in ohms. So every kind of wire will always have, no, a certain kind of resistance value. So again, no, this is how they change it, no. So from a proportionality symbol, when they remove the proportionality sign and make it into an equation, they added a constant there, no, just like when you're dealing with your math. So if you remove the proportionality sign there and make it equal, no, then you must add a constant. And in the constant that we added here is this seemingly, you know, this symbol that looks like letter P. And then this letter P now is actually called as our resistivity. So resistivity is similar to density, no? It's some sort of a unique property or value, no, for every kind of metal, no? And we are going to see a list of resistivities, no, for different metals, no, from copper, aluminum up to zinc, no. But maybe now we will just have a limited list because we have so many metals, no, that is there, no. So again, no, we add that resistivity symbol. So eventually resistance is equals to rho, no, or that letter P. We call it in Greek as rho. So rho L over the cross-sectional area A, no. So that's our, no, value R, no? Now this this resistivity that I was talking about, no, is listed now with this value, no. Now they say that this resistivities, no, is this resistivity values are true at a certain temperature of 20 degrees Celsius, because they also found that the resistance in the wire, no, is affected by temperature. There is a direct relationship of temperature to, no, to the resistance. The hotter the material, they discovered that it also possesses, no, a greater amount of resistance, no. So from this list, if you will try to examine, no, which resistance there, no, which value of resistance, which metal, no, has the lowest resistance or resistivity, and which material also has the highest value, no. So can you check the values there and tell me which one, no, is having, no, the smallest resistivity and the highest resistivity? Okay, Jason, what is the answer? What's your answer?
Ang lowest resistivity, sir, is silver, and ang highest, sir, is silicon.
Okay, very good, no. Now, what does that tell us about silver, no? So what does it mean, no? So it means that if the value of the resistivity is less or small, what is that kind of metal? Is it a good conductor or a bad conductor or poor conductor? Jason?
Good conductor, sir.
So most likely, no. So silver is probably, no, among the best conductor, or if not, no, the best conductor. Yeah, that's the metal here, no, that has the least, no, resistivity, no. So it means that when charges flow into silver, no, then they flow much more smoothly, no, or easily, no, than in other kinds of conductors, no. Now you've also mentioned about silicon, and I think silicon is a kind of a metalloid, no. So if you examine your table of elements, no, or your periodic table, you'll see them along the zigzag line, no? So you will see the silicon, germanium material to be along this zigzag line, and this zigzag line is telling us of metalloids These are materials that are both no, that are either no, they I mean no, they possess both metallic properties no, at some point, and no, they can behave also as non-metals no. So silicon no, so silicon probably is a good insulator no. But don't you know that silicon, when you provide it with the right voltage, there is what they call a firing voltage to silicon, that when you provide it no, as a semiconductor, it can also act no, as a conductor. No? It can become a conductor if you provide it with the right voltage. Now, at a different condition, it can become an insulator right away. No? So those are the functions of a semiconductor. And one material that is used for semiconductor devices no, is silicon and germanium. No? So these are two materials, and you'll notice that the resistivity also no, is among the highest from these lists. Now, I will also point out about tungsten, no? And I think tungsten, it does not really have a very small no, or a very high resistance, but it's not no, a very good conductor also. And I think no, I mentioned it that we use this for filament of bulbs. And as a filament in a bulb, no, it can withstand no relatively a high temperature. No, it does not break. So manotice nyo if the filament of the bulb breaks, no, amo nang ginatawag naton nga napunder ang bombilya, no. So if the filament of the bulb no eventually cuts no or breaks, then we will not see it lighting up anymore, no. So tungsten, however, no, is one material that can withstand high temperature, no, and can you can use it again and again, no, not like other materials, no. I think the symbol of tungsten is W. Now, another one that I would like to point out also is nichrome. Nichrome has one of the highest resistance also because its exponent is 10 to minus 6. 1.1, 10 to minus 6. And why will I mention nichrome? Because nichrome is, since it has a high resistance, you can use this now as an electric stove. If you coil it no into something like a wire no that is like a spring no or a coil of spring, and stretch it, connect it to a power source, you'll notice that the nichrome wire will glow no when you provide it with electric charges or current. So it will heat up. So if you put it no like or if you arrange it just like a stove no, you can actually cook something no in a nichrome wire. So nichrome wire is also no one useful metal no that can be heated up because of its resistivity. Now, resistivity again is one of the factors that affects no our resistance of the wire. No? So that's symbolized as rho. No? So it's something like letter P symbol. So length and resistivity and area are the three factors that we have no, for our resistance. So that's the resistance of a wiring. Now, the relationship of I and R, if you multiply it, no, it will give you the value of the voltage V. So VIR no, can also be written in this way. And this is an equation called your Ohm's law. Now, the guy again no, who made no or was able to coin the theory or the law no, is George Simon Ohm. He's a German physicist. Now, this physicist no, allows us to relate no, that if we divide the voltage by the current, no, V and R, we will get V and I, no, voltage and current. No, we will get a constant value, no, which is as seen in this graph, is a straight line. So this is a constant value, and if in mathematics, no, you can call that constant as the slope. No, here that constant R, no, which is the ratio of the voltage by the current, is known as the resistance. So that is seen in our equation of our Ohm's law. So please take note of our Ohm's law equation. So we can have it as IR. Others would call that value as I, if you will write it in terms of I to be V divided by R. No? So voltage over resistance can also be equivalent to the current I. No? So what is the unit of current? You can also write it as volts per ohm. No? Volts per ohm. Now, here is an expression or a sample problem. No? So what happens to the resistance of the wire now if you will stretch the wire 3 times its length? Now, if you are given, for example, a wire, no? So this is our initial wiring, no? Its length is maybe L, and what if we decide to triple its length by stretching it? No? You're going to pull it in such a way that it will get thinner, probably, most likely. No? Now, if in the process, if we will just simply elongate this, straighten this, or make this longer, let's say himuon mo nga 3 times longer. No? So if we are going to make this 3 times longer and we are not going to change, so man sabi 3 times longer than isa. So let's say that we will not change its size, same area, same dimension lang di. If you will simply increase its length, then maybe the solution that is provided in this problem may not be the correct solution. If we simply increase its length. So initially, if the length is only this much, if it's just the original length, the original length will give us a 5 ohm resistance. Now, if you are going to increase the length 3 times, make it now 3 times longer, then if each of these is 5 ohms, then we will know that the total resistance now after making it 3 times longer will simply be 15. It will become 15 ohms. Because again, each length is 5, so therefore if you add 2 more, then that will become 15. So again, still making, for example, the area to be the same, and the material is of the same material, so therefore finally it can become 15. Now, if however in the process, so if this is the starting dimension of the wire, and you're going to stretch it, kung imo siya nga butungon, so therefore maybe if you stretch the wire, then you can make the wire smaller. Okay, so another possibility, you can stretch it in such a way that it will now become 3 times longer, but in the process make the dimension smaller also. Okay, so do you follow? Since materials are ductile, metals are ductile, so maybe if there's a change in its area, then maybe we will consider 2 factors here. So however, if there's only one factor that we are considering, the length, then we can just simply multiply 5 times 3 to give us 150 ohms. Sorry, I think I should correct this. This must be this must be no, that's correct. That should be 15. 5 times 3, it's 15 ohms. Now, if there's a change in its area, maybe that's not anymore easy to follow. So if we stretch it maybe the area now reduces by 1/3. And if we check our solution here, if we have our length increased by 3 times, so the final length is 3 times the original length, and the area since it is now smaller will now become 1/3 of the original area. So these 2 factors that we now change, changing the area to 1/3 its original area, increasing the length by 3 times, no? So replacing the value, no, to R. So if R is rho, no? So that's rho L over A. And again, no, the final length now is 3 times the original one, no? So P dion, we have here 3 times of L sub O, no, original length. And our area now is actually equal to 1/3, no? 1/3 of the original area, because we reduce the area there, no? That we will now see, no, that our resistance, our new resistance now, no, will be now in this ratio where it will now become, no, 9 times the original value. So since 1/3 and 3, no, when you divide 3 by 1/3, that will now become 9, no? So that will be 9 times of the rho LOAO, no, which is the original resistance. So we will have there 9 times 5, no? So eventually, no, we will end up with a value that is 45 ohms. That is, no, if we consider the two, no, dimensions to have changed. So we will end up with this kind of analysis. Now, however, no, if we maintain, no, the lengths to be just simply the same, no, no, the area, I mean, not to be the same, then we will just increase the area there. No, now I think, no, that's the application of, no, our variables length and area and resistivity to this given equation. So we don't need to really substitute our value of rho there, no, for that given problem. No? We can actually make a simpler equations, no? If we are dealing with merely a change in length, and to the problem that we just answered moments ago, no, we can actually just simply use this ratio when we want to find, no, the new resistance given a new length, no? And if that's the case, no, so you can simply divide, no, R1, the previous resistance, by the new resistance, no, and you can simply equate that to the length, no, since the length is directly proportional to resistance, then you can just have the old length divide by the new length, no, and that ratio, no, can allow you to find the new resistance. Or you can also pair it, no, with the cross-sectional area. And since the cross-sectional area, no, is inversely proportional, then you can also use this. No? So our answer earlier about 15 ohms, no, can also be explained, no, by this ratio here. So if there's no change in the area, then you can simply cross-multiply these two values. So R1 times L2 is equals to R2 L1. And substituting the value, na, or solving for R2, then you'll have your L1 here as a denominator. And if the original resistance was 5, no, and the new length is 3 times, no, the original length. So if L1, no, is, or if the new length is 3 times L1 and the original length was L sub 1, then you can cancel L sub 1, no, the original length, leaving you 5 times 3, no, value to give us the new resistance to be 15 ohms. Now this one again, no, is only true when we maintain, no, the cross section to be the same, and the metal that you are using is also the same. Okay, so this is another way of answering, no, that given problem using this relationship, no, of the length and the area. Now I was thinking, no, about an example, no, of applying our resistivity value if we are dealing with a copper wire. Now, supposing we have a copper wire and we want to know the resistance of this copper wire, no, whose length is 5 meters. So it's 5 meters long. It has a diameter of 3 centimeters. we want to know how much resistance will our wire have. So if we go to this expression, no, that R is equals to rho L over A. Now, first thing that we need to know, no, is the resistivity of copper wire. Now, from our table, we will see that the resistivity of copper wire is 1.7, no, 10 to minus 8. So that's ohm meter. That's the resistivity rho. Now, if the diameter of that wire is 3 centimeters, then we can calculate actually its area or cross-sectional area by using the equation of a circle. Since the cross-section of a wire, no, is basically a circle, then the area of a circle is pi r square. Now, if the diameter is 3 centimeter, then we can express the radius to be 1.5 centimeter. But since the area should be in meter square, that we will have to express centimeter, no, in terms of 10 raised to minus 2, no, which is the equivalent of centimeter. And we will square the radius of 1.5 centimeter. So this one now, no, if you multiply this, no, will now give you the area of the wiring. Now, if the wire is 5 meters long, then we can now replace it now with resistivity times length over the area that we already solved. And then therefore, we are now able to get a product, then we divide that the total resistance of the wire is around 1.2 10 to minus 4 ohms. Now, we see that this resistance is so small, and it is expectedly should be small. Because again, our wire, guys, must not have a high resistance. Otherwise, it will heat up. So the importance or the significance of having a low resistance is that the wire will not heat up. Now, so again, that's the application of this equation here, which relates length and area together. Are you following me, guys? Thumbs up, please, if you have no question. So I see 5 people, 7 people. Their thumbs up, so that's good. Thank you for the feedback that you understand. Now, we also mentioned about the Ohm's law a while ago. And Ohm's law, as we say, is V is equals to IR. And V, guys, is voltage, or the unit is volts, and with some additional notations there, ampere for current and ohm for resistance. Now, we can actually we've seen our wire to have a resistance, but this zigzag line that I'm drawing here in my schematic diagram, so I have here a battery with a wire attached to this zigzag line, and again that zigzag line will also have a unit of resistance, but we call it as a fixed resistor. So this fixed resistor is not similar to the wire resistance that we have, but it is actually a resistor is actually a gadget that we will see, however, in our chapter 5 topic, that this resistor is useful in our circuit. So we purposely make a resistor that has a unit of ohms, resistance, and we integrate it with other circuit components to complete a specific circuit with some functions. Now, another way of looking at this resistance attached to our battery is an example. Could be thought of as an appliance or a load in your house. So a flat iron, a ref is considered as a load, or an electrical appliance. So this resistor here is probably representing some kind of a load, like that. A refrigerator, an oven toaster. So you can call it as R1 with that amount of resistance. Or again, that small gadget no that we see no in our previous no video on when we see no an example of a circuit. So again, no, this is a simple circuit, and the components of our voltage, current, and resistance are all found here. No? So we have here a fixed resistor, a battery, that will provide the charges, and then now, from the positive side, we understand that the current, when we provide it a path, will now leave the positive side of the battery, which is this longer length, and now will enter and will flow towards the negative side. So the negative side is the one that is indicated by this shorter line passing through the resistor. So question, how much is this current now that is flowing in our circuit? Now, if we know the principle already of Ohm's law, then we are able to calculate that current by dividing the voltage of 24 volts by the amount of the resistance that is present in the resistor of 12 ohms. So V divided by R will now give us the current I. So the current I will be now something like 2 amperes. So again, a unit of current again in amperes. So a circuit like this and with the correct maybe direction of current and our knowledge of the previous topics on voltage will now allow us to solve the value of I. So that's applying our concept of our Ohm's law. So we will notice here that we were able to calculate our resistance there. But another factor that we will try to check that affects resistance also is temperature. Now you'll notice that the resistivity value in our table earlier was set at 20 degrees Celsius because maybe at different temperatures, the resistivity value of the material may be different. So again, maybe it's important that part of the problem, the metal is indicated to be at 20 degrees Celsius before you can use those resistivity value. Now again, the idea is since temperature could probably fluctuate, it can go to a very high value that the resistance is affected by that directly. So higher resistance will eventually result whenever you increase also the temperature. So this is the temperature coefficient. This is how your resistance goes up every time you have an increase in the temperature. Now maybe not for carbon, because for carbon it's kind of negative. Every time you increase the temperature, then you will be subtracting a value to the resistance. That carbon now will have a lowering of its resistance eventually when you make it hotter. Just like germanium here because it's negative. But for copper, aluminum, they have a positive coefficient that when the temperature increases, we expect the resistance maybe not really that big, but the resistance will eventually increase by this much for every 1 degree Celsius increase in the temperature of the metal. So the metal will have an increasing value whenever the temperature also increases. Now we go next to this concept of the electromotive force. So the electromotive force or EMF. So this is the voltage that we get when we measure the voltage in a battery. So here is a battery and this circular device, this flat circular device that we draw here across this single cell battery, that what you are doing here is actually measuring the voltage in the battery. Now, if this battery will supply the current in this resistance, then the voltage, no, the EMF here must be higher, no, so that it can supply the voltage in the R sub E. R sub E, I think, no, is a resistance they call as the external resistance. Now, over here, there is a switch, no, that we can turn on and off. Now, when you push the switch, no, up and it is turned off, then there's no way that current can flow in the circuit. So whenever the switch is off, but still, no, despite the switch is off, if you use a voltmeter, no, and I think we see how it looks like, no, in our circuit construction kit AC, that the voltmeter will now allow us to measure the voltage in the battery here. No? Now, the battery alone, since it is not connected in the circuit, okay, the switch is off, that you will be able to get, no, the voltage in the battery called EMF. So that's the voltage of the battery when the battery is open, no, or the circuit is open. Now, that voltage probably will change when you turn on, no, the switch. That voltage in the EMF, no, will no from an EMF value will no longer be true, no, even if now we will keep the voltmeter in this location. So there would be two readings of voltages, no, whenever you turn this off or when you turn it on. Now, most likely when you turn it on, that value of the voltage will now go lower. Okay, it will now go lower or lesser. Now, there are two words here that we will be able to get, no, or the two voltages that we are going to get. First, the open circuit voltage, no, when the switch is off, which we will call as EMF, no, or the electromotive force. That's the voltage of your battery, no, when nothing is connected to it. Now, when you turn it on, what you will get, no, in your reading, no, is now known as TPD. TPD, no, is known as the terminal potential difference. And that is now the value, no, that you will get when you close the switch. That value must be smaller, no, than the open voltage, no, open circuit voltage of our circuit. So the EMF is denoted by something like this small letter E, no, you see this curve, something like number 3, no, in a reverse position. That is the value, no, or the symbol for the EMF, no. Again, it is short for the word electromotive force. We will now see, no, another situation wherein the TPD in this case, no, should be greater, no, because this time around the battery is not the one, no, that is providing current to the circuit, no. So the current is the one, no, that is entering your battery because you are charging your battery this time. So this time when you are charging, the TPD should be higher, no, than the EMF. Otherwise, if the TPD is not greater, you cannot charge your empty battery. Okay? So your equation here is EMF plus the voltage that is developed, no, inside the internal resistance in your battery. So again, this is in the charging process. So if your battery is 9 volts, so when you charge it, maybe, no, they will step it up to 10, no. So the one that is when you plug your charger, no, in an outlet, the charger is providing 10 volts, no, and it is charging a 9-volt battery, no, just like that in your phone. So it cannot be, no, that they will have the same voltage, because if they will have the same voltage, current will not get into your discharge battery. Okay? So amala na, no, I'm drawing that out because TPD, no, may mean the same word, no, but they will have two different values whenever you are using simply the battery to provide current on a load, and it will be different, no, when the battery is the one that is being charged. Okay, do you follow that one? So those are two, no, different So we will be moving on, no, and we are going to relate, no, some energy equations here, no. So we will have electrical energy, and I think, no, I've written this, no, when we start our lecture. That work, guys, no, is equals to voltage times charge, and current, no, as I've discussed earlier, is I times T, no. And then therefore, if Q is I times T, we can substitute it over this side. And eventually, we can write work, no, to be equivalent to VIT, an expression, no, that volts, ampere, second will give us, no, a unit called work in joule. Now, we can also write, no, aside from VIT, no, that if in our Ohm's law equation, if V can be written as I square, I times R, I mean, no? If V is equals to I times R, that if we replace V here with IR, so we'll have I times R, not times another I. So V alone again is IR, no? Then you still have IT here, so I times I gives us I square. So that will give us I square R actually, no, times the time, no? So this is another way of writing, no, our work, but it can come from this one, no, and combined with the notation of voltage. Again, now we can write also this Ohm's law equation in terms of I, and I is V over R. No? But if we will replace our current now in this equation, if I is V over R, you'll notice that V and V now will be found in the numerator, and you can actually square it. So we have V square times T, no? But you still have a denominator R, no? Which you can write over this equation. So here are three equations of our work, no, in joule. So it's either VIT, I square R times T, no? And V square T over R. Now we would probably remember, no, that we have accumulated those equations earlier, no? And let's see, no, how in what other way can we understand them, no? In terms of the equation that we just derived, no, where work, no, can be written as energy. So we define energy, by the way, as the capacity to do work. So therefore, work and energy can be we can use them sometimes, no, interchangeably. So if work earlier was equivalent to VIT, no, or we have there I square RT, or V square I, no, over R. So we have three different equations that if energy now can be written as VIT, no, and that work or energy, no, in our mechanics, no, ang work sa aton mechanics, we can also write it, no, as, okay. Now, sa aton mechanics, no, in our mechanics lesson in Physics 1, we define power to be work over time because 1 joule per second, no, is a unit called watt. Now, if you'll multiply the denominator time with power, so power times time actually is work. And work, since it is equals to energy, you know, so energy can also be written as power times time. Now, if energy is power times time, no, and this is our equation for energy, no, so you'll see that this is an equation eventually of energy, no. So VIT, no, is an equation of energy. Now T there represents time, and here is energy. So what is the value V times I? No? What do you think is V times I? If V times I, no, is a value that is multiplied to time, what does VI represent? No? So if you will look at this analogy below, so power must be equals to V times I. No? So electrical power, no, can be taken, no, by multiplying the product of the voltage and the current. No? So maybe, no, we can write it as P, no? And P can be written in terms also of I square R, no? So if you simply separate the value of time, you can have the remaining expression there for VI, or I square R to be power. Another way to write power is electrical power is V square all over R. So these are three ways to write your electrical power. Now, what's the unit of power again? It is expressed in watts, commonly. So 1 horsepower is another unit of power, guys, equals to 746 watts. Now, again, the product of power and time, watt second, is equals to 1 joule. But 1 joule of energy is not a very common expression of electrical energy, because what is commonly used is kilowatt, kilowatt hour. So in your electric bill at home, you will not you will not see a joule as a unit of your electrical energy, but kilowatt hour is a common unit, however. Now this expression here, we'll probably try to apply it in an application wherein we will have some appliances in our house, like a washing machine. Try to know its power rating in kilowatt, and then if you are going to use it for this number of hours every day, then how much is the power or the energy consumed by the washing machine. So washing machine is just one of the many appliances in your homes. You may have your flat iron, and usually the materials or the appliances that heat up, these are the ones that have a higher need for electrical power. Motors may not be that much, but usually heating equipments, electric stove, electric kettle, you're the one that you boil your water, water heater. So these are the ones that really would need maybe 1,000 watts, or 1 kilowatt in just one use, or higher. There are also some of our electrical appliances like a TV today that will also go up to 2,000 watts because of the many components that are inside our TV. Maybe in the olden TV, it's a very simple one, so it does not really consume a lot. But in today's TV, because of its attachments and the sheer size of the TV, that the TV may have a very, very huge amount of electrical power. Then if we convert that into a kilowatt, then maybe multiply it with the number of hours of use, then you will have your energy consumption of that appliance. So we will see that application maybe in our future discussion, that again we can calculate the cost also of energy use.